The regression line is going to be a line that goes through our data, and when we draw it, the idea is that as it goes through the data, it should be as close as it can possibly be to all of the points at one time. So with that, the idea would be if I start my line down here in kind of the middle of the data, it's like maybe I can get close to those values, but I don't want to ignore any values, so I don't want to really miss out on those down below there. So while it could start out going in this direction, maybe I'd have to adjust to be closer to down here. And just going through and thinking about how can I minimize this distance away from the line as much as you possibly can. So I'd imagine our line would go something like this, to be relatively close and follow the trend of our data. So this data here is based on our last example with distance from Baltimore and airfare. So we have our scatter plot, and then we can imagine this line going through, which would be our regression line. Some other names that you'll see come up for it is the line of best fit. You might also see least squares regression line is another name for it. Or like I said up above there, you might just see regression line. Basically in our course, if you're asked for the equation of a line, this is what you're looking for. This is our one and only line that we're really looking at in this class. So with this, we can get an idea of predictions. That's what this line is giving us, is predictions in terms of airfare. So then I could think about, well, if I'm going to travel 1,300 miles from Baltimore, what do I expect for the price? And we can get an estimate based on the airfare. So what we see from our scatter plot now are two values. We have the dots, which came from our actual data set. So we have these observed values. So let me even write this out. We have these observed values, which we call Y, and it's from our data. And then what we're going to have is coming from the line are predicted values. And these predicted values or predicted airfares, they relate to Y in terms of airfare. It's just we're going to save that symbol Y specifically for values from our data set. But for predicted values, what we're going to use is Y hat. We're going to put a little hat on top just to show that it's coming from the line. So we have these two values for Y, and the idea being if we focus on a specific X value, so let's say I'm here, I guess it's a little more than 600. This must be Chicago at 612. So when we have these flights to Chicago, we can see what we observed in terms of the price, which was $94. But then simultaneously, we can compare it to what we predict to happen. So we could compare these predictions of how does what we predict compare to what we actually observed. And this idea of comparison of those values are residuals. So what we could do is think about this vertical line between those two numbers there. If I think about this line here, and specifically the distance covered by that line, that's considered our residual, and it looks at this difference of taking our observed value, so our Y value from our data set, and subtracting it with our predicted value, which is coming from the line. So in the case of Chicago, what's happening there, let's see our predicted value, let's just say that's $150. So the idea being, if you're flying to Chicago from Baltimore, you might say, I expect to spend $150 on that ticket. But then what actually happened is you went to buy the ticket and you only had to spend $94. So what ends up happening here is that the prediction is higher than what actually occurred, which that's when we say we have an overestimate. Whatever resource we were using to predict that cost ended up being larger than what actually occurred. And that's going to happen with any of these values that are below the line here. If I look at these residuals in terms of comparing what was predicted and what actually occurred, even out here, is that our prediction was higher than what was actually observed. So these values that are landing below the line are going to lead to overestimates. And if we calculate this residual, like if I calculate the residual for Chicago. So we take the observed value, which was 94, and then subtract what was predicted, which is coming from that line, which I'm estimating is about 150. We get this negative value out, and that would be true for any of these values that are landing below the line. So if you find residuals for overestimates, that residual is going to come through as negative because you overestimated what would have occurred. If our values are landing above the line, like let's say we're here near 1200, which this must be Dallas. So we have Dallas here, which had an airfare of $278, and then just comparing it to what we're predicting, which in terms of a prediction, let's say it's like 210. So we're taking this observed $278 and subtracting this prediction of 210. Well, this is a case where if you know you're flying to Dallas from Baltimore, it's that whatever the prediction was, they say you're going to spend $210, but then you go to pay for the flight and it's actually $278. So that prediction was low. And that's going to be true for all of these cases here. You're going to get out these positive residuals, and that positive residual is coming from the fact that our estimate was too low. We predicted too low and had to pay much more. In fact, this case of Miami, you'd expect to spend about $200, and their ticket ended up being $350. So there was this big overestimate of what occurred. Underestimate. So that prediction was low. So when we land above the line, this is leading to underestimates. So they underestimated what would happen, and this occurs when we have positive residuals. So we're looking at this difference in outputs between observed minus predicted. Be sure you get the order correct here, that it always goes the actual value that was observed minus the value coming from the equation from the line. On the next page, we'll look at an example with this more clearly. What we're missing from this case is what if the data value lands right at the line, which we're kind of close with this low value at the bottom here. But let me just kind of make up a point. And let's say we had a point right here. So the line goes exactly through it. So this would be a case that in terms of a prediction, they tell you a prediction for the airfare. And then when you go to pay for the ticket, it's exactly the same. So this is a case where it doesn't underestimate or overestimate, it's exact. So when you land on the line, that prediction was exact, and that's going to occur when your residual, if we looked at the difference between those y values, it would just be 0. So that's the idea of residuals. I'm looking at this difference between prediction and what was observed. From there, let's go ahead and talk about the equation for the line, because we'll need this equation in order to look at these predicted values. So from algebra, if you remember the equation of a line, in algebra we describe it as y equals mx plus b. So we have our two variables, y and x, and then m represents slope of our data. So it's this rate of change as x changes, how does y change? And then b comes through as our y-intercept. It's like, where does our line intersect with the y-axis? That idea is exactly happening here as well. It's just our notation's a little different because we're in regression. So notation-wise, when we're working with a line, we like to use the symbol y hat to show that we have these predicted y values. Instead of m for slope, we use b with a subscript of 1. So we'll have the slope times x plus, and then for our y-intercept, we use b with a subscript of 0. So see that notation, but in terms of interpretation, same as what we see in algebra, in that what's multiplying with x is our slope, what's being added on as a constant is our y-intercept. So y hat is the predicted y value for a given value of x. b1 is slope, and in terms of interpretation, the sign of slope will give us an idea of whether we have a positive or negative direction. or you can think of its expected increase or decrease. So if slope is positive, we'll be seeing an increase. If it's negative, we're seeing a decrease. And in terms of a sentence structure, and we'll look at an example on this next page, how you can think of slope is if we increase x by 1 unit, whatever we're working with in terms of x, we increase that by 1 unit, then y increases or decreases by whatever we have for slope, so b1 units. I'll show you how this sentence structure applies when we have an actual value for it, but it's the idea of if we change x by 1, then slope tells us how y will increase or decrease, and specifically by how much as well. The y-intercept, so b with a subscript of 0, is telling us what happens when x is 0. What if we don't have a value for x? Then what is y going to do? So the idea is if x is 0, y is whatever that y-intercept is. So let's take these ideas and apply them to this case of working with that airfare data. So out there is a formula for how to find slope and how to find the intercept. But again, we're going to use technology because what we want to do is just get that equation for the line and then use it. That's more valuable. So first off, let's find this least squares regression line. We need to find the slope and intercept. So if we go to our data in GeoGebra, so here it is from when I was working on that previous page. You don't have to go to statistics to do that. So what you'll need to do is plug in the data and then get to that 2-variable regression analysis. Then once you're here, if you look at the bottom of our scatter plot, you can see this regression model right here. And then there's this drop-down menu of it's set on none, but then you can see linear, log, polynomial, so many others, but we're doing linear. So if you go down to regression model and then select linear, it'll draw the line for you. So now you can see the exact line of best fit. And also at the bottom here, you can see your equation of the line. Now they use y, but we want to, when we write this down, we'll want to use y hat, but then you can see your slope, you can see your intercept. Sometimes here, it doesn't show you enough decimal points sometimes. So let me show you how to make sure you want 4 decimal places. It's more accurate. If you go to the upper right here, and sorry, it's actually off the screen, but those 3 horizontal lines that opens up this menu. So if you hit those 3 horizontal lines and then go down to settings, you can see rounding, and changing that to 4 decimal places will help a lot. I believe I showed this in a previous video, but I set that and then I saved my settings. So now whenever I open up GeoGebra on my computer, it always does it. But if you set that to 4 decimal places, then you'll see enough information here. So there's our equation of the line. So here, so getting that least squares regression line, we're using GeoGebra. And what we found is y hat is equal to 0.1373 times x plus 81.7636. Another way to write this that you might see is actually using the name of the variables. So like y is represented by airfare. So what we could write this as is like the prediction for airfare. So airfare with a little hat equals 0.1373 times distance plus 81.7636. So you might see these least square regression lines written like this sometimes using the actual name of the variables, and it can be helpful when you're doing a lot of interpretations so you know which is your x and which is your y and what it represents in context, but writing it either way is fine. So the slope of our data. So the slope is always the value that's multiplying with x. So slope, which we're going to write as b1, is the 0.1373. So what I want to notice is that this is positive. So we're seeing this increase happen. So fitting that sentence structure that I outlined here, if we increase x by 1 unit, so x in our case is distance. So I could say, like, it's the idea of if we want to travel 1 mile further. So if we increase distance by 1 mile, by 1 mile, so if we just change that by 1, so that fits the, if we increase x by 1 unit, y increases or decreases by b1 units. So I'd say y, which is airfare, capitalize it, airfare, and because it's positive, it's increasing. So it increases by, and then we're going to take our slope, so 0.13, and then units, which for airfare is money. So this is the equivalent of like $0.1373, which is like 14 cents. I could say is by about 14 cents. So the idea being that as we increase our distance, our airfare is going to bump up by about 14 cents each time as we increase by 1 mile. So that's fitting the sentence structure. So if we increase x by 1, then y is going to change by whatever our slope is. And then we just want to make sure we use the units that match up with x and match up with y. So interpreting slope, you can always do. Interpreting y-intercept, this sometimes doesn't make sense. We'll just go for it and talk about it. But sometimes when you try to do this, it doesn't work in the context of the scenario. So sometimes you can't interpret the y-intercept. Slope, you can always interpret. Y-intercept is kind of a special case. So y-intercept from our data is the 81.7636. So this is the idea of if x is 0. So if distance is 0, this would be our airfare. And that's a little strange if we interpret that way. In fact, I'll write it out. It's like if the distance is 0 miles, the airfare is $81.76. Now interpreted like that, that doesn't make sense. You don't, like, I'm not flying anywhere today. I'm traveling 0 miles from Baltimore. I'm not going to suddenly get charged $81.76. However, what we could think is for someone buying a ticket without having any sort of distance added onto it, they're paying this $81.76 each time they buy a ticket. So what we could interpret this as in this case is like a base charge. It's like those extra fees or taxes that they add on with it. So we could interpret this as the base charge for a ticket. It's like this amount will always be part of the ticket sales. So this, it takes a little thinking to get there. The cases where it doesn't make sense, most often you could have a y-intercept that's negative, and with that, I would just not even interpret it. I would just say the y-intercept does not make sense in context. It was coming out to be negative. It doesn't mean our line is incorrect. It's just sometimes doesn't make sense to interpret it. All right, part D here. Estimate the cost of a ticket if they are traveling 200 miles from Baltimore. So what we're doing here is we're being given a value for x. And what we want to do is estimate the airfare. So we want to find a value for y hat. Now, what we could do is use our formula up above there. Really, that's what we want to do. If I want to estimate my airfare for 200 miles, I would use that equation of the line and find my value. And that is perfectly correct. But something I want to show you, and it does kind of depend on the data we're working with, is at the bottom of GeoGebra here, you'll see this symbolic evaluation where you can plug in a value for x. That's exactly what we're doing here. And the GeoGebra function here is more accurate. And like I said, it just depends on the data, but sometimes there can be somewhat large difference between the two values, and GeoGebra would be better to use. So you can use either, just show your work and I can follow along, but what we could have done is just skipped writing it out and just go to GeoGebra, type in 200, and get out that value for y, which I think this is pretty close to what would come out if you used a calculator with your formula. But if you just need to find a lot of these, like if x was a certain number and you need y, you could just use GeoGebra to get those out. So it's 109.22 for airfare. So I'd say is if we travel 200 miles from Baltimore, the airfare is expected to be $109.22. And something I want to emphasize here is the wording I threw in there, because I wouldn't want to say the airfare is $109.22. This isn't an observation, we're making a prediction here. So we'd want some wording there that the airfare is expected to be, or the airfare is predicted to be, or we estimate the cost of the ticket will be. We need some wording in there saying that this is a prediction of sorts. It isn't an actual observation of what the ticket cost. So, which airfare has the largest residual? So this is something that we could see visually if we imagine those vertical lines between our dots and the equation for the line. Here is basically all of our residuals. And to have the largest residual would be the furthest away, which is coming from this data value right here. So to figure out which one this is, you'd want to go back to your data set and see where was X kind of close to 900-ish, and then we had a very large ticket sales, which I believe came from Miami. Just to jump back to our data set, what we're looking for here is in terms of close to 900, we had this 946 and 998, but Miami was the one that had this large airfare. So the largest residual is coming from Miami. But let's actually calculate the residual since we haven't practiced that yet. So Miami, in terms of what was observed, we had a distance of 946 and airfare of 350. So that is our X and our observed Y value. So then I need the predicted, because in terms of residual, what I want to take is the observed minus the predicted, or rather my Y value minus Y hat. So for predicted, what we're going to use is the same value for X, because I still want to go to Miami. So that distance is set in stone, but what I need to find is what is the predicted airfare for going to Miami. So we're going to use as our formula, or if you want to go ahead to GeoGebra and just plug in 946. So I'll go down here and just type in 946, and I can see this 211.61 as the predicted airfare. To make sense in terms of the picture that we were looking at, our prediction was pretty close to 200, and our airfare was much larger from the actual observed value. So from that, we can get our predicted airfare of 211.61. So the value of the residual, what I'm going to take is the observed value, which was 350, minus the predicted value of 211.61, which is 138.39. So we're getting this positive residual out, which means we had an underestimate. means our predicted value was lower than what we actually observed. It's like if we were, you can kind of put yourself in the shoes of the traveler. If we were going to Miami, it's that we had some resource that said, yeah, you're going to spend about $212 for this ticket. But then when you go to buy it, it costs so much more. Your prediction, and whatever source told us that prediction, we might be a little angry at them because then when we went to buy our ticket, it was actually $350, not $212, and nowhere even close to $212. So with that prediction model really underestimated. So you could say for the ticket to Miami, the linear model underestimated airfare. The linear model underestimated airfare by, and then that amount of money. Underestimated airfare by $138.39. So you can get an idea of how far that model was off from what we actually observed. So that's what we can do with our equation of the line. We can find it in GeoGebra. We can interpret slope and interpret y-intercept. And interpreting y-intercept only really works some of the time. And then from there we can talk about residuals and making predictions using that equation of the line.